So let's have a look now at the finite cardinal numbers. So this is fairly straightforward. So we start off with E0, an aggregate E0, which consists of a single element E0, and we simply define 1 to be equal to the cardinal number of this particular aggregate. And now if we take E1, a new aggregate, to be the union aggregate of E0 and a different element E1, we can define 2 to be equal to the cardinal number of E1. So then we can find E2 to be E1, the union aggregate E1 and E2, and define 3 to be equal to E2 cardinal number, and we can continue this process. So we get 4 is equal to the cardinal number of E3, for instance, and we can continue this and get nu is equal to the cardinal number of E nu minus 1 in general. We can also see in general that E nu is going to be equal to the union aggregate of E nu minus 1 with a different element E nu, which can be written as E0, E1 up to E nu. And it also follows from this that the cardinal number of E nu is equal to the cardinal number of E nu minus 1 plus 1. So this really comes from the definition of addition of cardinal numbers that we defined earlier in the video. Okay, so that's this gives a sequence of numbers, obviously 1, 2, 3, 4, nu, and on. It's an unlimited sequence, so there's obviously no greatest cardinal number here, but any aggregate that has a cardinal number that is 1 in this series is said to be a finite aggregate, and these are defined to be the finite cardinals. So there's just a few theorems just to mention really relating to these finite cardinals. One of the theorems I'm going to spend a little bit of time in particular dealing with, but I'm not going to go through all of them. So theorem A is the terms of the unlimited series of finite cardinals are all different from one another. That's not really surprising to us. Theorem B, every one of these numbers nu is greater than the preceding ones and less than the following ones, as we kind of expect. And C, there are no cardinal numbers which in magnitude lie between two consecutive numbers, nu and nu plus 1. So there's nothing, as far as we're concerned, in terms of cardinal numbers, there's nothing in between any of these numbers. If we start at 3, the next cardinal number is going to be 4, and there's nothing in between. Okay, so theorem D is one that I just want to spend a little bit of time working through. I've got a few comments that I just want to make on that. So this is theorem D from section 5 of Cantor's first article, which says that if M is an aggregate such that it is of equal power with none of its parts, then the aggregate ME obtained by addition of a single new element E has the same property. In other words, it too is not equal in power with any of its parts. Now the reason that this is to me an important theorem is because it really proves what we'll see is a characteristic property of finite cardinals in comparison to transfinite cardinals. So the finite cardinals, finite aggregates, are not equal in power with any of their parts. Now here we've we come back to this ambiguity regarding this notion of parts with this particular theorem. So here, if M is an aggregate such that it is of equal power with none of its parts, then presumably we cannot mean that M itself, we can't consider M itself as a part of M, which is kind of in contrast to the theorem that I mentioned earlier, which kind of suggests that M can be considered as a part of itself. So again, it's really down to the context. Maybe more specifically here we could say if M is an aggregate such that it's of equal power with none of its proper parts. Maybe that would be a more appropriate kind of description, but that's what we've got to work with. So let's have a look at the proof of this theorem. It's a fairly straightforward one. So suppose that N is a part of ME. So we get two possible cases here. Either N contains the element E, or N does not contain the element E. So we're going to consider these two cases separately. So if N contains E as an element, then N can be written as M1 E. Okay, and now let's assume that N is equal to, in power, to ME. So N is a part of ME. Let's assume that it's equal in power, which does imply that it's actually going to be equal to ME itself. So therefore we get that ME is equal to M1E. So because these are equal, they must be equivalent. So equal aggregates are, in an obvious sense, equivalent aggregates. So therefore there must be a one-to-one correspondence that we can find between these two aggregates. And the one-to-one correspondence that we choose, we're going to choose in such a way that it keeps E fixed. Okay, so we correspond E with itself in both aggregates. Well, in that case then, our one-to-one correspondence will also be a one-to-one correspondence between M and M1. So these kind of partial aggregates of these two. So we've got a one-to-one correspondence between M and M1, so M must be equivalent to M1. But because they've got the same elements, because all of the elements of M1 are elements of M, and similarly all of the elements of M are elements of M1, then we've got that M is actually equal to M1. But this is the more important thing, because this tells us that the cardinal of M, cardinal number, is equal to the cardinal number of M1. But M1 must be a part of M. So this contradicts the hypothesis that M is not equal in power to any of its parts. So it can't be that N is a part of NE of equal power with ME and containing the element E. So that's the first case, the first contradiction. So now if N does not contain E as an element, still under the assumption that N is a part of ME and N is equal to ME, then either N is a part of m, or n is equal to m. But either way, we can write n equals m1 f. So m1 is going to be a part of m. It's either a part of m or it's a part of m, but because this notion of part it's a transitive relation in a kind of obvious sense, then m1 must be a part of m in either of these cases. It doesn't make any difference. So again, we've got n equals this and n equals this, so therefore m1 f must be equal to me. And just like we did before, we can find a one-to-one correspondence between these two, because with them being equal, they're also equivalent. We can find a one-to-one correspondence which maps f to e and vice versa, and therefore we'll get that m1, there is the same one-to-one correspondence restricted to m1 is going to map to all of the elements of m1 to all of the elements of m and vice versa. So m1 is going to be equivalent to m, again even equal to m, but more importantly we can say that m1 cardinal number is equal to cardinal number of m. But m1 was a part of m. So again, this contradicts the assumption that m is equal in power with none of its parts. This is saying that it is, therefore we've got a contradiction. So in both cases, if n is a part of me, whether n contains this e as an element or whether it does not contain e as an element, it cannot be equal to me, and therefore any part of me is not equal in power with me itself. So we're kind of going up to the aggregate with the next cardinal number. So from m we get into the next cardinal number with this me, and we're showing that that cardinal number itself, any aggregate with that cardinal number, has the same property. And as it turns out, all of the e news that we defined previously, when we were talking about the introducing the finite cardinal numbers, all of these have this property. And because these are the aggregates that we use to define the finite cardinals, then it means that any aggregate any aggregate that has a finite cardinal number must have this property, that it can be equal with equal in power with none of its parts, or proper parts if we prefer, which is going to be in contrast to when we get onto transfinite aggregates and transfinite cardinals. It's going to be a very different situation. So this theorem then is used to prove theorem A, which I mentioned before. So theorem A was that all of the finite cardinal numbers that we've defined are all different to one another. There are a couple of other theorems that I just want to mention in here. So we've got theorem F, which is that the finite cardinal numbers are well ordered. So the specific wording is if k is any aggregate of different finite cardinal numbers, there is one, kappa sub 1, amongst them which is smaller than the rest and therefore smallest of all. And theorem G, which says that every, I'll write down some notation for this, so every aggregate k, which equals kappa of different finite cardinal numbers can be brought into the form of a series k equals kappa 1, kappa 2, kappa 3, such that kappa 1 is less than kappa 2, is less than kappa 3, etc. And that wraps up all of the theorems from this section on finite cardinals. So next we're going to look at the transfinite cardinals. So moving on now to transfinite cardinals. Well, we define any aggregate as being a transfinite aggregate if it doesn't have a finite cardinal number. So now we need to show that there are actually transfinite cardinal numbers, cardinal numbers that are not finite, in other words. So let's take the aggregate of all of the finite cardinals, nu, and let's take this being an aggregate itself, we can take its cardinal number, and we're going to write this as Aleph naught. So what we need to show then is that Aleph naught is actually is not a finite cardinal, and therefore it's one of these transfinite cardinals that we're talking about. And this is fairly easy to show because if we take now the aggregates of all of the finite cardinals and then just stick another element in there, then this is equivalent to the aggregate of all of the finite cardinals, and this is not difficult to see at all. So roughly speaking, if we write out the elements of this aggregate as E naught, 1, 2, 3, 4, etc., and the elements of this aggregate as 1, 2, 3, 4, 5, then we can see that we can just map the elements very easily in a one-to-one fashion. So it is a one-to-one correspondence between the two, and therefore this aggregate must be equivalent to this aggregate here. But the cardinal number of this aggregate, so nu E naught, the cardinal number of that, by the way that we defined addition, is going to be Aleph naught plus 1. And over on this one, we get the cardinal number of this to be equal to Aleph naught, by what we wrote up here. But because they're equivalent aggregates, then these must actually be equal. In other words, we get Aleph naught plus 1 is equal to Aleph naught. And it's this that shows that Aleph naught is indeed not a finite cardinal, and therefore one of these types of cardinal number that we classify as a transfinite cardinal. Because if this were a finite, if Aleph naught were finite, then Aleph naught plus 1 would have to be different to, this would effectively be the next number along in the sequence of finite cardinals. And as we've seen in the previous section, all the finite cardinals are different from all of the cardinals that they're not equal to. So in particular, a finite cardinal is different from the next one along in that sequence. So this would be the next one along effectively from Aleph naught. So if Aleph naught were finite, then this couldn't be equal to this. Aleph naught plus 1 could not be equal to Aleph naught. So therefore Aleph naught is a transfinite cardinal. So it's good to know that at least we've got something that we're talking about. So just because we said what a transfinite cardinal was didn't actually mean automatically that any existed. But at least we've got that now. And it's fairly easy to see and to show even that Aleph naught is going to be greater than nu for any finite cardinal. And not only that, Aleph naught is going to be the smallest transfinite cardinal. So in other words, if A is a transfinite cardinal and A is not equal to Aleph naught, then we get that LF naught must be less than A. And this is the next theorem that I'm going to prove from this section, theorem A. And I'm wanting to focus on this theorem just for a few minutes because historically it is quite a significant theorem. It's been the source of quite a bit of controversy. So I'm going to go through this theorem in a little bit of detail now. So I'm just going to go through the theorem now that's written on the board, which is every transfinite aggregate T has parts with the cardinal number LF naught. And I'm going to refer to the book. I'm going to quote more or less from the book for this one for a good reason, because the wording is the important aspect of this proof. There's a point that I want to make that's depends really on the wording. So it says, if by any rule we have taken away a finite number of elements T1, T2 to T nu minus 1, there always remains the possibility of taking away a further element T nu. So therefore the aggregate T nu, where nu denotes any finite cardinal number, is a part of T with the cardinal number LF naught, because T nu is similar to nu in the obvious kind of way. So therefore T nu cardinal number of T nu is equal to the cardinal number of nu, which is equal to LF naught. And that finishes the proof of that. But this is quite a controversial theorem and proof. So in modern terminology, we'd say that every infinite set has a countable subset. Where is the problem here? Well, the problem is with the selection of this, because we're told that these are chosen according to some rule. But then Cantor just says, well, then there's the possibility of us choosing another element. But he doesn't explain how the rule is to be extended to this element, the next one that's selected, the one after that. We're just able to somehow select an arbitrary number of, a countable number of elements from T to form this aggregate here. And this is the problem. In general, the rule can't be extended. And this depends on the axiom of choice. In modern mathematics, not such a problem. Such dependence on the axiom of choice is fairly normal, but around Cantor's time, this was quite controversial to do this. This is what's called an implicit use of the axiom of choice. The axiom of choice wasn't a thing at this particular time when Cantor published this work, but he is using the principle that we would recognize as the axiom of choice, or more specifically the denumerable axiom of choice, in really getting to this aggregate here. So over the decades which followed, so the first half of the 20th century, this was a big thing, a big issue regarding this axiom of choice. A lot of mathematicians just flatly rejected the axiom of choice, others embraced it. There was a lot of disagreement regarding the axiom of choice, and that makes this quite a controversial, although seemingly innocuous, quite a controversial theorem when it's put into the context of the time that it was written and in the couple of decades which followed. From a modern perspective, it's nothing. It's perfectly normal, but at the time, it was a big deal. Okay, so then we've got theorem B, which says that if S is a transfinite aggregate with the cardinal number LF naught, and S1 is any transfinite part of S, then the cardinal number of S1 is also LF naught. So I'm not going to prove that. I just want to go through some of the properties now of this Aleph naught. So we've already seen, for example, that Aleph naught plus 1 is equal to Aleph naught. Well, I can add 1 again to each side of this, so I get Aleph naught plus 1, well actually it's going to be plus 2 now, equals Aleph naught plus 1, which is equal to Aleph naught. And continuing this process, I get that Aleph naught plus nu, for any finite nu, is going to be equal to Aleph naught. Then by separate means I can extend this to Aleph naught plus Aleph naught, which is also shown to be equal to Aleph naught. So it's not simply a case of just continue this process to get to this. This has to be shown by separate means. But again, I can go through a similar kind of process. I can add Aleph naught to either side of this. This can be written, by the way, as Aleph naught times 2. Not equals. So I get Aleph naught plus Aleph naught plus Aleph naught is equal to Aleph naught plus Aleph naught, which equals Aleph naught. So this is Aleph naught times 3, which using commutativity as well, I can write as 3 Aleph naught, and this as 2 Aleph naught. So I can continue this process again to any finite cardinal here, or here indeed, to get that Aleph naught times nu is equal to nu times Aleph naught, which is equal to Aleph naught. Again, we've just got the finite term in here. And I can continue this process. So I can get to Aleph naught times Aleph naught equals Aleph naught. So once again, this has to be shown by separate means to the reasoning that I used here. It doesn't automatically follow that if this is true for all such finite nu, then it must be true for this as well. This has to be shown by separate means. But I can write this as Aleph naught squared, and similarly I can get Aleph naught cubed, which is Aleph naught times Aleph naught times Aleph naught, which is, I can think about as multiplying each side of this by Aleph naught. A lot of Aleph naughts flying around. And similarly, I can show that Aleph naught to the power of nu, where nu is any finite cardinal, is equal to Aleph naught. So these are just some basic properties of this Aleph naught, this smallest transfinite cardinal. So we've already got the first transfinite cardinal, Aleph naught, sussed out to a certain extent, and this is the smallest transfinite cardinal as we've seen. Cantor says, without really elaborating, on it too much, that from this Aleph naught we can get another transfinite cardinal, Aleph 1, which is different to Aleph naught. In fact, it's the next greatest transfinite cardinal. And in a similar way, from Aleph 1 we can get the next greatest transfinite cardinal, Aleph 2, and we can continue this up to Aleph nu, and for any finite cardinal number here. But that doesn't exhaust all of the transfinite cardinals. If we were to continue in this way, okay, we'd be able to get more and more and more of these transfinite cardinals, but actually we can take the limit. Again, he doesn't elaborate on this at this stage, but we can postulate the existence of what we call Aleph omega, which is kind of the limit cardinal of this sequence. But things don't stop there. We can go to the next one, Aleph omega plus 1. So omega, as we'll see further down the line, is an ordinal type which we've not really got onto yet, but just think of it at this stage as the first transfinite cardinal after all of these ones. So we can continue in this way as far as we want, and then we can get to Aleph 2 omega, and we can continue this process as much as we want. So there are an infinite number of these transfinite cardinals, and this is what we're kind of working towards developing this theory. Although it's going to move more onto ordinal types and ordinal numbers, this does come into it as well further down the line. So that about wraps things up for this video. There's nothing really more for me to say on cardinal numbers at this stage. The next section moves on to ordinal types. So I want to thank you for watching this video, and I look forward to seeing you in the next video.